And we're live. Okay. So hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Sorry. Today we have the honor of having Dr. Cullan Howlett, a research fellow at the University of Queensland. Dr. Howlett is an expert in mapping the positions and motions of millions of galaxies in our universe to uncover how it has evolved since the Big Bang. His research seeks to uncover the dark sector using the largest galaxy surveys in the world. He's an active member of the Dark Energy Spectroscopic Instrument Project, the Wallaby Project, which is based in Western Australia, as well as Foremost. Dr. Howlett also works on simulations of the distribution of galaxies, their properties, and how fast they're moving away from us. He then compares these results with real data to extract information about the dark matter and dark energy, and also to look for discrepancies. Today, he'll be telling us about his work for galaxy peculiar velocity surveys. Dr. Howlett, thank you so much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
Okay, great. Thank you. Yeah, thanks for the invite and the kind introduction. I'll just share my slides. Yes, okay. So, hi everyone. My name's Cullan Howlett from the University of Queensland. And today I'm going to be talking to you about measuring cosmology and cosmography with galaxy peculiar velocity surveys. And so the outline of this talk will be basically trying to convince you that the clustering of galaxy positions and motions will allow us, or does allow us, to test gravity on the largest scales in our universe, to map our local neighborhoods, and to constrain the properties of dark matter and dark energy. So I'll start off with some motivation. So why do we want to test GR or other gravitational theories, and why do we want to make these maps? Why are peculiar velocities in particular good for this? I'll give a bit of a flavor of what we do once we have these peculiar velocities, some current constraints that we've obtained, and then what we hope to achieve in the future with some of the surveys that test, such as Desi, Foremost, and Wallaby. Okay, so let's start with something that should hopefully be familiar to some of you. So this is the theory of general relativity that was created or theorized over 100 years ago now. And this is our current theory of gravity, and it gives great testable predictions within the solar system. And so one of its really early successes was to basically correct the discrepancy that was seen if you use Newtonian gravity in measurements of the precession of the orbit of Mercury. And once GR came along, that basically gave a very exact prediction for that, and something which basically, if you combined Newtonian and general relativistic corrections, gave something which was very, very precisely aligned with the measurements at the time. However, in the last 100 years, we found that GR plus the luminous matter that we see in the universe cannot be the full explanation. In particular, we found two components that we still don't know what they are. One of these is called dark matter, and evidence for this comes from things like galaxy rotation curves, the anisotropies in the cosmic microwave background, and in the positions of galaxies. And then we also have a phenomenon called dark energy, whose presence is derived from distance measurements using supernovae, but also nowadays with other forms of distance measurements, such as those coming from large-scale structure probes. And basically, we're in a bit of a quandary now in cosmology, which is, due to the fact that basically 95% of our universe is required to be made up of this dark matter and dark energy, but we still don't know what they are. And so that means that 95% of our universe consists of what are currently unknown particles or fields. But one alternative could be that general relativity requires a modification on large scales, and that might help to alleviate some of these problems, or at least provide an explanation for what we're currently calling dark matter and dark energy. And this kind of motivates us to test general relativity in less well-explored regimes, such as scales outside the solar system, and in particular on cosmological scales where these two phenomena, dark matter and dark energy, seem to appear. And we want to compare those predictions of GR to other predictions from other models as well. And either we can confirm GR on cosmological scales, or we can falsify it and help to provide some route to an explanation for these two components. And so this is even more timely, given that there's currently some tensions between different probes that should be measuring the same cosmological parameters. So here on the left, I'm showing measurements of the matter density of the universe on the x-axis and sort of the strength of clustering, of galaxy clustering on the y-axis. And you can see that a bunch of measurements from what we call weak lensing probes are these colored contours here, yellow, red, and blue. And they are somewhat discrepant with the predictions from early universe probes extrapolated to the present day, which are shown in gray. An even more stark tension, which I'm sure many of you are aware of, is the Hubble tension. And so this is a tension which arises basically if you compare early universe probes again, so in particular the same survey Planck, which is measurements of the cosmic microwave background, or Planck, or even weak lensing plus other distance measurements, such as from large-scale structure, alongside early universe constraints from Big Bang nucleosynthesis. And you find that those results are discrepant with late-time probes that use basically very local measurements to constrain the Hubble parameter, for instance, from using supernovae. And so we know that GR works well in the solar system, so we want to test it on large scales. And we can do this actually with large surveys of galaxy redshifts, and as I'll also tell you in this talk, also with measurements of pure velocities. So this is a map of the field of galaxies around us. And this is actually a reconstruction built using pure velocity data. But what I actually want to start off with is what we actually observe. And what we observe in real life is this quantity called redshift. So we get this from taking spectra of galaxies. And this redshift actually has two primary components. The first is the cosmological redshift, which is due to the expansion of the universe. And the second are these peculiar velocities, which sit in the center, and these are sourced by gravity. And so by using these velocities, either directly or indirectly, we can actually directly test our gravitational theory. They provide a direct link to a particular gravitational theory. This is even more apparent if you look at the equation of motion. So this is basically one of the first equations which drops out from the Einstein field equations. And you can see that this is a pretty simple equation. But what it basically does is it says that the velocity of a galaxy, which is on the left-hand side here, is related to the density near a galaxy purely by these proportionality factors. And this proportionality factor here, F, is called the growth rate of structure, and it has very strong predictions from general relativity. This is basically what GR predicts for that constant. And they find that it depends only on the amount of matter in the universe and time. And in particular, it gives very strong constraints on this gamma parameter, which is set to 0.55. And it also predicts that it doesn't change with scale. So that means that it doesn't change with the size of the object that you're looking at. You'll see there's no X dependence in here, basically, so it should only depend on time. And so these are two pretty strong predictions that we can use to test. And so that means if we have a set of densities on the right and we have a set of velocities on the left, we can compare those to constrain this growth rate of structure, and we can use that to try and constrain different gravitational models. So there's two ways that you can get these velocities, basically. The first is a technique that many of you may have heard of, which is called redshift space distortions. This is kind of the workhorse for measuring large-scale gravitational models, and has been used, quite a lot over the last 20 years to produce really tight constraints on the growth rate of structure. But there's also another method, which is this direct methodology, which is something I'm going to talk about here, which is using the actual peculiar velocities themselves and then looking at how those are correlated with each other. And so the difference between these two really is that the redshift space distortions are an indirect probe, whereas on the right, the peculiar velocity measurements are a direct probe. And I'm going to be showing quite a few graphs like this one on the right in this talk. So for those of you who are unfamiliar, this is called a power spectrum. On the right-hand side, where there's large K is small scales. On the left-hand side is large scales. And you can roughly treat this K here as 1 over a distance. And on the y-axis, we're just talking about how much correlation there is, basically. So it's basically the amount of correlation as a function of scale. Okay, so let's start with redshift space distortions. So showing this equation here again, the way redshift space distortions work is that we basically take this equation here and we assume that on the right-hand side, these cosmological redshifts should be isotropic. We basically assume that the expansion of the universe should not have any particular direction. And so that when we observe galaxy positions from the observed redshift on the left, the velocity here acts as a contaminant. But conveniently, that contaminant can also be used as a signal. And so what happens is if you were to infer the position of a galaxy using the observed redshift, you find that on large scales, objects tend to be moving towards large clusters. And that means that along the line of sight, so given by these two arrows here, you find that objects start to appear squashed when you use their observed redshifts, but you treat them as if they were the cosmological redshifts. And so these velocities pull the inferred positions of galaxies towards the clusters and give this apparent squashing along line of sight. And on small scales, because galaxy velocities are effectively random, they're random and uncorrelated, they can be whizzing around in all particular directions. And if you average over that, you find that on small scales, you get this elongation of the clustering. And so when you measure the clustering of galaxies using the observed redshifts, you find a very particular pattern in the clustering. And from that, you can infer the strength of gravity. So this is an example from a simulation, I think, of those effects of those redshift space distortions. So on the right, you can see the positions of the galaxies that you would get if you used cosmological redshift to map them. And on the left, you see the impact if you use the observed redshift, which are contaminated by the peculiar velocities to map them. And you see that on large scales, things have got squashed. And on small scales, you've got these elongations that we call fingers of God. And so the clustering that you infer from galaxy redshifts depends on the angle to the line of sight as well. So clearly here, because our redshifts are only along the line of sight, along this direction here, the inferred position is the same for galaxies which are falling sort of sideways, but is different for galaxies which are falling inwards. And so this amount of anisotropy, how distorted these otherwise spherical distributions are, tells us about how fast gravity is acting. So here's an example of the correlation function measured from, I think this is averaged over many simulations. Actually, no, I think this is data. This is data. And so here I'm showing the strength of the probability of finding two galaxies separated by some distance transverse to the line of sight and along the line of sight. And you can see exactly that pattern I just described earlier. So on large scales along the line of sight, you see the squashing effect, but then right in the center, you see this elongation due to the sort of small scale clustering. And so the way we then can constrain the growth rate of structure is we can Fourier transform this map and we can compress it based on the angle to the line of sight. And you might find something like this. And so here, these different lines are just different components of the angle to the line of sight. So here this top one here is where you've basically done a spherical averaging. Here is where you've done some averaging where you weight it by cos theta squared. And this is cos theta to the 4 effectively. And by looking at the difference between these amplitudes, we can actually constrain, the amount of clustering or the amount of anisotropy in that clustering. And larger growth rate, so larger gravity or stronger gravity, means that you have more anisotropy and you have larger differences in the amplitude here. So that's one way that we can get handles on measuring the growth rate of structure. And this is a really common technique, and it's been done basically many different surveys over many different redshift epochs in our universe. And that's because redshifts are pretty easy to measure over a large cosmological volume. However, at low redshift, this information actually saturates, and that's because we actually only have one universe to measure. And so we can only obtain a certain amount of information, no matter how many redshifts we observe. Here's an example of some of the measurements of the growth rate of structure here, which I've normalized by this sigma 8 parameter as a function of redshift. And these are from many different surveys now. Some of them are independent of each other, some of them are not. So you can't necessarily do a chi by eye fit here. But what you do see is that you can compare them to the different predictions from different models of gravity, and in particular, GR is this gamma of 0.55 model. And there is some potential hint that at least the standard lambda CDM plus GR picture is not quite favored by the data, but really it's too early to say with the current measurements. But in particular, low redshift, where this information saturates, that's where you start seeing the biggest differences between these gravitational models, especially if they're anchored at high redshift by the Planck constraints from the CMB. And so an alternative, which actually overcomes the saturation, is to use the direct measurements of peculiar velocities. And so this is tricky, and historically it's very tricky, but nowadays we have some very large samples becoming available, which will enable us to produce very accurate measurements of the growth rate of structure beyond what you can obtain with just redshift space distortions at low redshifts in the local universe. Okay, so why are peculiar velocities useful for this? So typically, we have way less peculiar velocities than we do redshifts. I'm not even sure how many current redshifts we have. It's almost certainly in the tens of millions now with current data sets. But if you compare that to how many peculiar velocities we only have about 55,000 current peculiar velocity measurements. So in terms of pure numbers, it may seem like this is a completely useless endeavor. But actually, each one is worth far more in terms of cosmology. And that's for two main reasons. The first is if I look at this plot that I showed you earlier, where we're trying to measure the sort of amplitude difference between these different lines. If you actually look at the models for this, you find that not only does it depend on the growth rate of structure, which is this F parameter shown here, but it also depends on this parameter called B, which is a nuisance parameter that we have to deal with. And so this amplitude difference actually depends also on this unknown parameter we call the galaxy bias. And it arises because we're trying to infer the properties of gravity luminous matter to measure. And we know that luminous matter only makes up about 5% total matter. And so the fact that we have to marginalize over this bias significantly weakens our constraints because it enters at the same order as the growth rate of structure. However, for pure velocities, the clustering is effectively bias-free. And the reason for this is because the velocities are driven directly by gravity. They don't care about whether it's the luminous matter or the dark matter doing the gravity. And so if you were to look at the same models for the velocity field, you find there's no galaxy bias entering in there. So here's an example of this. So what I'm showing on this plot is effectively the same set of measurements, but now I'm measuring the power spectrum or the clustering of velocities. So there's no galaxy redshifts necessarily here. This is just the how correlated two velocities are. And you see that you can do the same trick and you can compress them and look at different angles compared to the line of sight. And you find that in both cases, they're only proportional on large scales to the growth factor. There's no B in here. And so the second reason these are very useful is that actually you can, this probe here actually can be combined with the redshifts themselves. And so we find that if you were to look at the clustering of the density of the positions and of the velocities, you can actually combine them to overcome the saturation of information in the local universe. And this is because they both effectively have the same PM term, which cancels out. And so this is useful because precision comes for free with a velocity. If you've measured a pure velocity, you've already got a redshift as well. And so if you have a set of 55,000 pure velocities, you can actually already do this cancellation, which you can't do if you have 10 million redshifts and no velocities. The downside is that each pure velocity measurement actually has extremely large uncertainties. So this is often about 20% of the recession velocity, or on order of several thousand kilometers per second, on a measurement which we expect from theory should only be a few hundred kilometers per second. So that means you need a lot of pure velocities in a very small volume in order to average out this random error. But luckily with current surveys or upcoming surveys, we have started to achieve this. Pure velocities are also essential or very useful for other aspects of cosmology. For instance, if you want to do transient cosmology, so trying to measure the Hubble diagram using supernovae or gravitational waves, as is shown in this paper, you actually need to correct the host position for that pure velocity. And that's because the Hubble diagram, you need the cosmological redshift on the x-axis, but we only have the observed redshift. And so having accurate pure velocities is essential for this correction. And as I showed in this paper, if you choose different measurements of the pure velocity, you can actually move your posterior on the Hubble constant from this single gravitational wave event by quite a substantial amount. And so the correct thing to do really is to average over that. You can also do this really cool stuff with velocities, for instance, by looking at maps of our local universe. And so this is a paper from last year where the authors here took the pure velocity data sets that other people had produced. And they then, I think, trained a machine learning algorithm on the velocities from a bunch of simulations. And then they applied that algorithm to the data and were able to reconstruct what looks like a large filament in our local group, which connects our galaxy at the cross to Andromeda and also to the Coma and Fornax clusters as well. And so you can use these velocities to get really detailed maps of otherwise hidden structures in our universe. So this is, effectively all dark matter here, which you could not see with just by looking at the galaxy positions. And here's another example of that. So this is from a paper a couple of years ago, where again, velocities were used to reconstruct the density distribution in our local universe. And here you can see the distribution of effectively flows in our universe. So each of these arrows corresponds to effectively a flow line of a galaxy moving through our local universe. And you can see that the local universe really is a complicated map of sort of densities and motions. But by measuring the velocities and the redshifts, we can start to reconstruct this map and start to look for interesting features in there as well. So how do we do this? How do you measure a pure velocity? So for a pure velocity, what you need is a distance indicator. And you need that because you can measure the observed redshift, as I said earlier in this talk, very easily from a spectrum. But in order to isolate the pure velocity, you need an estimate of the cosmological redshifts, which you can estimate from a distance indicator. Many of you will have heard of perhaps the most famous distance indicator, which is a type 1a supernovae. And so you can use type 1a supernovae to get pure velocities. However, type 1a supernovae are pretty rare. So what we use in practice is, at least for the larger samples, is these two relationships. And these are the two that I'm going to focus on here today. But if anyone has any questions about using supernovae for this as well, please do ask me. And so the first is the Tully-Fisher relationship, which is a relationship between the rotation speed of a galaxy on the x-axis and its true brightness. And so once you have an estimate of its true rotation curve, basically, a rotation speed, you can read off this graph to get an estimate of its true brightness. And you can compare that true brightness to the apparent brightness, and that gives you a distance. And so really the pure velocity here, once you've made a plot like this, you can effectively read off as the offsets between a data point and the red line. And we treat that as the pure velocity. You can do the same for elliptical galaxies as well. It's a little bit more complicated because it's not a 2D relationship like the Tully-Fisher relationship. It's a 3D relationship. This works for elliptical galaxies, but the essence is the same. So what we do is we take a measurement of the velocity dispersion, the surface brightness of an elliptical galaxy, and its radius. And if you were to plot this for a nice clean sample of ellipticals, you find they all lie on this plane in this 3D space. And then you can fit this plane, which is given by this red line here. And by comparing the offset between the predicted size from the red line and the measured size of a given galaxy, that also gives you a measurement of the pure velocity as well. And that offset, and the pure velocity again is directly proportional to that offset in the size axis here. And so the largest single catalog of pure velocities we have now is they call this SDSS Pure Velocity Catalog. It was released earlier this year and contains about 34,000 pure velocities over an area of about 7,000 square degrees. So this means that it's not full sky, but it is very, very dense. And it does go to higher redshift than any previous pure velocity catalog as well. So here's the comparison of that SDSS Pure Velocity Catalog alongside other existing data sets. And so the SDSS Pure Velocity Catalog kind of sits in the northern galactic cap up here. And then in the southern galactic cap, we have the 60F survey, which is in red. And then the Cosmic Flows 4 Tully-Fisher survey also contributes about 10,000 of the known pure velocities to date in green, and that's more full sky. And so if you add these three up, you can see you get pretty close to the total number we have today, which is about 55,000. We also have some supernovae and some other types of distance indicator, which contribute to that total number as well. And you can see that these are really actually quite complementary data sets. So the Cosmic Flows Tully-Fisher methodology works best at very, very low redshifts, but provides a lot of objects down there. And then the 6-degree field and also the SDSS surveys are both Tully-Fisher samples, fundamental plane samples, and they tend to work best at high redshift. And the new SDSS catalog really extends our coverage to higher redshift here. And so in particular, this one catalog is nearly twice as many as any previous survey, or all previous surveys, combined. So before this, we had just 60F and Cosmic Flows 4. Okay, so how do we build this catalog? So we first select some data from SDSS with an R-band magnitude limit. This is very important that you know the R-band magnitude limit well to correct for selection function biases that can arise in the pure velocity measurements. We then also apply additional cuts to make sure we're definitely getting early type galaxies or ellipticals. We verify they don't have any active star formation so they can sit on the fundamental plane nicely, and that we're accurately able to measure their velocity dispersions, which go into the fundamental plane from the spectrum. And so for certain observations, sometimes you just don't get good enough signal to noise to be able to measure velocity dispersion, even for a galaxy which should fit on the fundamental plane. And so we are forced to discard that. We also produce a bunch of simulations that replicate all aspects that we could think of for that data. And we use this technique, which is basically some sort of halo abundance matching / HOD style technique to populate these simulations. And so these simulations are designed to reproduce the clustering of the data. So this is this is the clustering of the redshifts in the data, where the points show the data and the line shows the average of the mocks. And they're also designed such that if you fit each of these 2048 simulations with the fundamental plane model that we're using on the data, you can plot these distributions of those fundamental plane parameters. So these are all the parameters of the model for that plane in the fundamental plane space. And you find that the data, which is the red line, is well represented by the distribution that you find from those simulations as well. And so the simulation is really useful because we can then use them to basically quantify every single aspect of our analysis pipeline. So we, like I said, we use these mocks to validate how well we recover the peculiar velocities. So when I talk about peculiar velocities, I'm going to be talking about this parameter called eta here, which is effectively proportional to the peculiar velocity, although not quite. You have to basically take this and you have to multiply it by redshift to convert it to a peculiar velocity. But you can see that basically on the y-axis, I'm showing what we would observe from the mocks if we run it through our pipeline against the truth from the mocks. And you can see they sit on this one-to-one line almost perfectly. And this is really important to validate because a very small offset from this one-to-one line can actually correspond to a very large peculiar velocity. So these numbers here correspond to the peculiar velocity that you would infer if you had a small offset from this one-to-one line. And it's very, very bad if you have, for instance, a curve which dips down to here and is coherent across all the simulations, because it means that you're always going to be measuring a constant peculiar velocity out of your survey of 400 kilometers per second, which can completely ruin your cosmological constraints. There are also residual data systematics, which we can correct for empirically. So for instance, we found that there was a trend between this peculiar velocity quantity here and the richness of a group, which we, as of yet, are still not fully convinced where that comes from. We're not sure if it's physical, just because galaxies in different group sizes, for instance, might have slightly different properties, or if it's because of some unknown systematics in the data, for instance, that surface brightnesses are harder to measure for galaxies at high redshift or in richer groups. And so we're not quite sure which of those it is, but we are able to empirically correct this just by splitting the data up into these different group richness bins and fitting separate fundamental planes in there. So how do we actually use these peculiar velocities? So now we have this enormous catalog now, 34,000 from SDSS plus another 20,000 from these other data sets if we were to combine them. And so the first thing we can do with a set of peculiar velocities is we can actually just maximize the likelihood of observing a set of those velocities. And this is what we applied recently in a paper by my student to the SDSS data. Another method is that we can basically treat them exactly like we did for the redshift space distortions, and we can Fourier transform them and compress them and combine them with these redshift space distortion measurements. And we've applied this to previous data, including the 6-degree field data and the 2-mass Tully-Fisher survey. So here's an example of the data that we have now, where for each, what we've done basically, we've taken the entire observed universe that we've observed with these peculiar velocities in them, and we have gridded it up into cells, and each cell we basically averaged the densities of galaxies in the top panel and the average the velocity as well, or what we call this eta parameter, which we call the log distance ratio. And you can effectively either then Fourier transform this and compress it, or you can just try and fit it directly. So the first method is to try and fit that directly. And so here you're looking at the field of overdensities and peculiar velocities as a function of separation, and you're then comparing that to a theoretical likelihood, which contains information on the growth rate of structure. This is actually really simple in principle. So what we do is we just say, okay, well, imagine we've got those distribution of observed velocities and overdensities is given by a Gaussian distribution, where this is the observations, and all of our theory is absorbed into just the variance or the distribution, the covariance matrix of this field. If you split this up, you split up into 4 parts, basically. You're looking at the covariance matrix, or the likelihood of finding 2 galaxies separated by some distance in redshifts, 2 velocities separated by some distance, or a galaxy position and a galaxy velocity separated by some distance. The utility of this technique is kind of shown by this expression here. So this is just for the CVV part. And you can see that this is a useful way of measuring the growth rate of structure, because the growth rate of structure sits right here. And in particular, if you remove the K dependence, so we assume that it is constant, you can pull it all the way out the front, and it's very, very easy to fit for that growth rate of structure. So your cosmology dependence enters into these C terms, And this W term here really just depends on the geometry of your survey. So it just depends on how a galaxy at position I is related to a galaxy at position J. In practice, the model is actually far more complicated than that. It requires you to account for what we call wide angle effects. So this is to account for the fact that the lines of sight between two galaxies, particularly at low redshift, are not parallel to each other. You also have to account for noise in the two fields. So in the density field, in the redshifts, we have Poisson noise because of the sampling of galaxies. We also have the velocity error, pure velocity errors, so the 20% error on each pure velocity measurement we have to account for. We also need methods to model nonlinearities and to speed up the evaluation and the fitting, especially for these next generation data sets. Ultimately, all of that can actually be absorbed into your covariance matrix here. So it means that you have to come up with some complicated expressions here where you kind of grid the data and you include errors and you include nonlinear modeling components as well. But nonetheless, the whole pipeline, this whole fitting methodology has been validated again on these SDSS simulations. So here you can see a set of measurements of the growth rate of structure measured from simulations. We actually use two methods to speed up the fitting. And in both cases, they give consistent results centered around the theoretical expectation from the simulations. If we apply that to all the mocks, we find that we recover a distribution centered around the truth with a relative uncertainty, which is consistent with the data as well. So we apply the same technique to the data, and we basically find a constraint on the growth rate of structure, which is shown both in the left panel as the red and blue lines, and also in the right panel as the contours. And the kind of interesting one here is this F sigma parameter. And you find we get relatively tight constraints, which are consistent with the expectation from general relativity, which is given by this dashed black line here. And so these other parameters here are really just to deal with nonlinearities in the modeling. But the key result is that we are consistent with GR according to this data. So the second methodology that we can use is to compute the anisotropic clustering of the velocities in the same way as we would for redshifts. So we first take the redshifts of each data point in the pure velocity sample, we convert it to a distance, we grid it, we Fourier transform it, and then we count the power spectrum amplitude in each cell, and then we average. And if you do that to the redshifts that I presented earlier, you find the same plot that I showed earlier. But if you do this to the velocities, what you instead find is something we call the momentum power spectrum. This is not quite the velocity power spectrum. It's called momentum because you only have velocities where you have galaxies. And so it's more like a density times velocity power spectrum. And this is what that looks like if you test this on simulations. And so this is from a paper that we put out in 2019, showing the distribution of velocities, or the momentum power spectrum, sorry, as a function of scale. And also showing that if you account for enough complexity in the modeling, you can actually model this to very high accuracy as well. So on large scales, this is proportional to the velocity power spectrum. So this is just linear theory here. But as you go to smaller scales down here, you have to start accounting for things like nonlinear redshift space distortions and also some other cross terms as well. But the key aspect is that the actual amplitude of both of these, so really just the y-axis scale here, is directly proportional to the growth rate, or at least the growth rate squared. And so it's almost possible to read off the growth rate from these graphs, and that makes them very, very powerful to constrain the growth rate of structure. So in this paper in 2019, we took some of the current state-of-the-art data at the time, the 2-mass Tully-Fisher survey and the 6DF field survey, and we stuck them together and we fit both the momentum power spectrum in the top and the density power spectrum in the bottom. And we use that to constrain the growth rate of structure as well. So here's an example, or a plot rather, of the growth rate of structure measurements that we obtained from that work, shown as the red points as a function of redshift. And again, some other methodologies are shown here as well. And really, the takeaway from this is that our result is, again, consistent with GR, but slightly lower, just like a lot of the other measurements currently in the literature. But also, if you were to look at some of the other data sets here, basically every one of these other data points here, so this one, this one, this one, the red one, D19, and C15 and S18, I think, are all using the pure velocities in some way. And so really the direct velocities really help us to fill in this area below redshift 0.1 compared to the redshift surveys, which tend to populate the area up here. Okay, so moving on from cosmology, I want to spend a few minutes talking about cosmography. So curiosity surveys, because they're sensitive to the total matter in the nearby universe, they enable us to produce some really interesting reconstructions of our nearby universe. And so this is not cosmology in the traditional sense, but it's kind of cool because you can use these maps both just for, cartography, just like, the ancient sailors were interested in mapping the Earth. We can also try and do the same thing with mapping the nearby universe. But you can also use these reconstructions to correct for transient positions at low redshifts. And you can also use them, for instance, for galaxy evolution, because you can start using these reconstructions as probes of environments, for instance, in which the galaxies live in. So you can imagine looking at the environment of a galaxy, not just in terms of its nearby number of galaxies, but potentially the nearby density of dark matter, reconstructed from the velocity field. And so this is an example of one of these reconstructions, which uses the peculiar velocity data. This uses, again, the same sort of 2MTF plus 6DF plus a few other sets of data. And here we're showing in red and blue is the density of matter reconstructed only from the velocities. Overlaid on top of that are the redshifts that we've measured in the local universe as well. And so it's worth saying that these black points that are shown in this plot are not used to reconstruct necessarily the underlying density field, but you do see really good agreement, basically, where you see an overdensity of galaxies, you also see an overdensity of the underlying total matter distribution. And you can really pick out some of the sort of main features of our local universe in these maps. So with the SDSS Curiosity survey, we've started looking at this as well, and we can actually extend our coverage by a factor of more than 2 in the north. So here's a plot of that same sort of map. So here I'm showing in red overdensities and in blue underdensities. And again, the black points that I'm showing here were not used necessarily for this reconstruction. Some of them may have velocities, and so they would have been used, but really the black points here are from a separate independent redshift catalog that I've plotted over the top. And the green line here shows the extent of that previous map that I just showed you. And so what this enables us to do with this data is really push out our cosmographic analyses. And now we can capture some really interesting structures which we know are there from the redshift surveys. For instance, this structure here is the Sloan Great Wall. And so with these new cosmographic maps, we can really start to look at detail about the flows and the underlying structures that make up this Sloan Great Wall, for instance. And so that's cosmography. And just to wrap up and I've talked a lot about the SDSS Peculiar Velocity Survey, which was released this year, but I also want to spend the last few minutes talking about what we're going to do with future surveys. And in particular, surveys like Desi, Foremost, and Wallaby, which were mentioned at the beginning of the talk. And so just like the SDSS Peculiar Velocity Survey has really helped improve by several times the number of peculiar velocity measurements we have, and also the volume they cover, future surveys are actually going to go an order of magnitude even beyond this in terms of the number of galaxies and the volume they cover. So here is a very rough map of the kind of distribution we expect from these data sets. So this sort of nice looking contour sort of map here in the center is sort of the limits of our current reconstructions. And they're based, for instance, on the surveys like the 2-mass redshift survey and the 6-degree field galaxy redshift survey. But over the next few years, we're going to be having these surveys, in particular from Desi, the Curiosity survey, this survey called the Foremost Hemisphere survey, which is going to act in the southern hemisphere, and also Wallaby, which is a bit more shallow, but also will act in the southern hemisphere, but is a radio survey, whereas these Desi and 4HS surveys are optical, and so really allows us to capture those galaxies that we would otherwise miss in the optical surveys. And you can see that we've started to push out into this area with this new SDSS catalog, but really that's only a sort of a fraction of what we hope to achieve with these future surveys. And these all started. Well, sorry, Desi has started, Wallaby has started, 4HS is expected to start mid-2024, but planning and preparation and construction of that instrument is all working really well and all at pace as well. And what I haven't shown here as well is, for instance, LSST supernovae, which will also be groundbreaking for peculiar velocity studies, and it's something I'm very interested in, but won't touch on anymore in this talk, really. So just to give a bit of an idea of what Desi is and what it's doing. So Desi is located in Arizona. It's an instrument on the Mail telescope at Kitt Peak Observatory. It has this fiber positioner, which has 5,000 fibers. And it's basically the first stage 4 large-scale structure experiment. The aim is to obtain over 40 million galaxy redshifts between redshift 0 and 2. It covers about 14,000 square degrees. and has up to 5,000 fibers on the sky at the same time. It really is kind of the premier spectroscopic instrument we have available to us now, and probably almost for the rest of the decade. And it recently finished taking its first year of data. So I'm also involved in some of the analysis using the large-scale structure data, which I haven't talked about in this talk, but if you're interested, you can, of course, email me or ask me a question about how that's progressing as well. But for the purpose of this talk, what I want to talk about is the fact that we're also carrying out a peculiar velocity survey on this instrument using some of the spare fibers and also some of the main survey targets where those are suitable as well. So we're hopefully going to be putting out a paper on the target selection for this survey early in the new year. And so here's an example of the number of galaxies we expect to get from the Desi peculiar velocity survey. In green, I'm showing the Cosmic Flows 4 data I showed earlier. Red is the 60F data, and blue is our new SDSS peculiar velocity catalog. And the Desi, for the first time, actually will be a survey which hopefully will enable us to have both fundamental plane galaxies in dotted and Tully-Fisher relationship galaxies in dashed lines from the same survey. And their complementarity is such that if you combine them, you get this amazing density of galaxies, basically far and above what we have from any of the other surveys to date. We've also forecast the growth rate we expect from this. And by combining the Desi redshifts from the Bright Galaxy Survey and the peculiar velocity survey, we expect to get very, very tight constraints on the growth rate of structure in narrow redshift bins below redshift 0.2. And this will be complemented by all the other higher redshift measurements that Desi will get just from its redshifts alone. And the power of the peculiar velocities is such that if you didn't have these, the redshift survey from BGS alone would have very weak constraints because there's just not much universe there to measure. But by combining the redshifts and the peculiar velocities, we can overcome the saturation of information at low redshifts, and we can get very, very tight error bars. And so LSST could potentially go even further as well. So that's because each supernovae has far, far better distance measurements than each galaxy. If a supernova has a 4 times or 5 times better distance measurement than the galaxy, effectively it's worth 16 to 25 galaxies in terms of its contribution to our measurements. And so here is all I'm going to say about LSST, but we also put out a paper about this in 2017, where we showed that if you have LSST supernovae, you could potentially get very, very good constraints on the F sigma rate as well, over many, many different redshift bins. And in fact, the improvement you get from peculiar velocities no longer stops at redshift 0.2, but because the supernovae are better individually, if you have enough of them, you can also start using peculiar velocities to improve your measurements at higher redshifts as well. But this really, really does depend on our transient and host follow-up capabilities, which are still very much uncertain, I think, for LSST. And so I want to just end with this slide covering basically some of the surveys that I've mentioned. And so the future in this field, I think, is very, very bright, especially if everything goes to plan over the next 5 years. And if you sum up all these numbers, we're looking at basically on the order of over 45 million redshifts from these 3 surveys, as well as over 600,000 peculiar velocities that we expect to measure. And that should be compared to, the current state of the art in peculiar velocity, where we've got maybe 50,000, 55,000. So this really is an order of magnitude increase in the number of velocities. And also it's worth saying an order of magnitude increase in the number of redshifts as well. And so the question is, I think, after 5 years, will we have found any evidence contradicting lambda CDM and GR, or will we have confirmed it? And so hopefully, if you invite me back in a few more years, we'll know the answer. Thanks.
Thank you so much, Dr. Howlett, for the very interesting talk. So we now have time for questions from the audience. You can raise your hand here, or you can put the question in the chat and I'll read it out. And if you're watching us from YouTube, then you can put your question in the chat, also put the question in the chat. Go ahead, Miguel.
Hi, do you hear me? So thanks, Cullan, for the nice seminar. And I have a question. So if you go in the momentum power spectrum approach, where you try to measure the momentum P of k, then as you showed in your paper, as you go to higher and higher k's, you get no linear terms because you have cross terms of delta and v, right?
Yes.
And in principle, also, at some point, you will also get nonlinear bias corrections, right? Just like in the effective field theory, one loop corrections.
Yes.
So how much do you think is still needs to be done to understand this in terms of theory, and how do you we plan to parameterize this to push to smaller and smaller scales with velocities?
Yes, that's a good question. So one of the things I said early on in the talk is that the velocity is effectively bias free, and that's true only on linear scales. As you start going to nonlinear scales, not only do you have these cross terms, you're right, you also might have to start worrying about things like velocity bias. So maybe the velocities are not perfect traces of the matter field. In this model, I did not include any of that. For Desi, it may be that we'll have to start worrying about that. It really is something that I haven't looked into and needs testing further, because it's really going to depend on how, what the error bars are like down here with surveys like Desi. Because it may be that the statistical error down here, due to the velocity errors and the shot noise and the measurements, is so great that we don't have to worry about it too much, because if we assume there is no bias, for instance, it doesn't introduce a significant systematic error above the statistical error.
Right.
And
I guess that will depend a lot if you're doing fundamental plane or if you're doing supernovae.
It does,
and,
yes.
Yeah,
for instance, for supernovae, it may be more of a worry, because the thing that dominates the noise down here on the error bars on these measurements is the velocity errors. And, as you know, the supernovae are far better in terms of individual velocity errors. But it's the velocity error squared over the number density. So it's a really delicate balance between how many objects you have and what the average error on each one is. So it's a complicated thing, but I think one of the things that we're currently looking at, or will be looking at in Desi, is methods to improve the modeling here. And that's something that I'm working on with people. For instance, that's one of the reasons why I'm visiting Princeton at the minute.
Right, thanks.
Thank you. Do we have any more questions? Reinaldo?
Hi, Cullan. I really enjoy your talk. I would like to come back to the FPs as a function of cluster size that you have shown.
Yes. Yeah, that was an intriguing result.
Yeah, that's very intriguing. Yeah. How much it depends on the sigma, from the cosmological models, for example, because it seems to me that could also work as a probe for, let's say, non-homogeneous cosmological models, for example. Could you comment about that, please?
Yeah, so this we found, so we didn't find this in the mocks. That's what I was saying. So this plot here is only for the data. And so the fact we were not able to reproduce this in the mocks, the issue with the mocks is that the n-body simulations there are only approximate. I don't even trust the group richness that you would measure from the simulations that we have produced. The fact that we see this in the data, though, I mean, in order to use this for cosmology, you'd have to be confident that this is a signal. And at the minute, we're not confident either way. There's been lots of hints in the literature that this could be due to physical effects in galaxy evolution. For instance, it could be that galaxies in richer groups have different assembly histories, and so they actually populate slightly different fundamental planes compared to galaxies in weaker groups, I guess. And so if that's the case, then conceivably there should be a way where you could just add some other parameter to your fundamental plane, make it a four-dimensional relationship, and it would automatically account for this, and also potentially improve the errors on your velocity measurements. But the other very likely or equally likely scenario is that this is actually systematic in the data. For instance, because you only measure rich groups at low redshift, because you're more complete at low redshift. And so there is a redshift dependent effect here. So you're not perfectly magnitude limited, for instance, or in rich groups, you have intra-cluster light, which affects your velocity, your surface brightness measurements, for instance. And so these things, if someone was to take the data and wanted to look at that in more detail, I'd be very happy if they were willing to do that. The data is all online, and all the mocks, and everything that someone would need to carry out these tests is all online. So yeah, it'd be interesting if someone wants to do that.
Okay, thank you. I'll take a look at that. Okay, thank you very much.
And do we have more questions? Let me just check in the YouTube chat also. Okay, I don't see anything there. Hey, now, do you still have your hand on? Do you have another question? Okay, I see you didn't. Okay, sorry, let me just check the chat because everything just disappears. Okay, so if any of our junior members want to ask a question in the chat, I'll be happy to read it out. If not, okay, so if there are no more questions, we'll wrap this up. The presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Howlett. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar. And happy holidays.